So what we have here, I've got a curve graphed. It's the sine of x squared between negative pi over 2 and 3 pi over 2. It doesn't really matter what the curve is. What matters here, this little triangle here, that's showing us what the slope of the curve is at that point, or the slope of the tangent line at that point. So at this point right here, the slope is 1.79. So then this point right here, this little diamond or the sideways square, that's the point on the derivative. So this right here is the x value that we're at, and then the slope of the function itself at that point. Okay? So if I move this point A to, say, right here at 0, the slope is going to be 0, which means that the derivative is going to have a value of 0. Or if I move A, I'll move it to another 0 here. If the slope of the tangent line here is 0, it's actually where I am a little bit off of 0, then the derivative is going to be equal to 0. And you can see that when we're on a downward slope, this point here goes below the x-axis. If we're on an upward slope, the point here goes above the x-axis. So it's set up in a way to show me what the slope of the tangent line is at any point. So what I can do now with this is going to let us see what the derivative looks like, is I can just move A. I can move A along here, and we can see that this point on the derivative is tracing all of the slopes. Now, it's skipping some of them, so we can see that we can see here, it's pretty easy to see that this is continuous. And this is the main idea I want to get across. For most of the functions that we're going to deal with, we're going to be able to take the derivative, and that derivative is going to be continuous. And so in this region right here, where the dots are kind of spread out, that's just happening because the derivative was moving very quickly. And so between the 2 points on the curve, or the 2 points that it used, there's some space. But if I use points between that, it would fill in those gaps. Okay, so if we look at the derivative, which is the one that point traced here, and we look at the function itself, we can see that when the slope of the function is negative, like in this region right here, then the derivative is below the x-axis. When the slope is positive, the derivative is above the x-axis. When the slope is 0, anywhere we have a maximum or a minimum, we get a 0 slope, at least with a smooth curve like this. So like right here, the slope is 0, the derivative is 0. Right here, the slope is 0, the derivative is 0. Right here, the slope is 0, the derivative is 0. Okay, so we have this relationship between the derivative and the function itself, and we get this continuous function. So from this smooth curve that we started with, we get a derivative that is also a continuous function and a smooth curve. Pretty cool, huh? The point here is, and I already said this, but I want to say it again, make sure that you get it. Most of the functions we're going to deal with are not only functions themselves and continuous functions themselves, but are going to have derivatives that are continuous functions. And actually, since the derivatives are continuous functions, guess what we're going to be able to do with those? Take the derivatives of the derivatives and take higher order derivatives. So we could take second derivatives and third derivatives, and well, that's a little ways down the road.